All right, guys, let's get started. Okay. So this is week 3, I think, right? Um, so today, several things. I'm gonna give the first homework assignment, couple of homework assignments, and we're gonna start our first pretty advanced topic, which is large language models. Um, so I'll talk. So you guys are section 2, so I haven't created the assignment link yet, but I will be doing that over the weekend probably. Um, and I'll give that to you. So we've covered ML word problems, right? And we've covered tensor operations, and I'm sure by now you've gone through these 110 operations at least like 3 times, right? All right, so I'm assuming you're doing those. Today we're going to start, what I called building a baby Chat GPT or a baby GPT, I should say. So it's essentially like a large language model that I have compressed to like the minimal code for us to understand it. Okay. And so we're going to build from there. So I'm going to create a module here. I'm going to call it baby GPT, baby GPT. And I already have the repo on GitHub. So I'll link that in. And so essentially today, we're not so much looking at the whole algorithm of a GPT and a large language model. We're still just looking at the tensor operations involved. Okay. And then eventually we'll start building up. I'll give you the link should be here for you to read. But we're going to start. Yeah. So this should go about here, tensor operations, baby GPT. So that's going to be the module. Okay, and the link, the repo should be in here. This one, how LLMs work. So this is the one actually that I put together for this. And this is what we're going to cover today. So let me just add that link to Brightspace. I'm just going to state the code. All right, so there we are. Go back to table of contents. So, a large language model is a really complex thing, right? It's something that don't expect to understand everything today. We're understanding just the building blocks of it. But you will see I have a very short version. I think it's like 20 lines of code, of a GPT. And we'll build up from there. So yeah, so we'll focus on this today. So you can see I'll click here. And that takes us to what we'll be doing. I'll use Colab just to demo some of this. All right, so before I do this, then let's talk about the homework because this ties in. They're both like related, right? So what is the homework assignment? So it's actually 2 homework assignments that you will have. Remember that this is a grad level class, so these are more, longer homework assignments, more involved. So the first, but they both go together, right? So homework 1 is essentially to build a crawler or scraper, right? So that you can download text from the internet. Does that make sense? So that's essentially what I'm going to ask you to do. And then homework number 2 is you will use that data that you downloaded to pre-train a GPT. Okay? So, a couple of things. So when you train something like a Chat GPT, you pre-train it on all the data in the world, like the whole internet, all the books. That's called pre-training. And then you do fine-tuning, and that's really where it starts to become like a really good model. So don't expect your model to be great as ChatGPT is or something like that, right? That's not the goal of this task. The goal of these assignments is to see how difficult it is actually to build one of these models, but at the same time to go through everything, right? Because here's the thing, you know, it's think about how technology was in the 70s, right? And compare it to today. So what if in 10 years you can actually train something because technology just changes, right? So what you're not getting, the thing that you're missing is all that data, but you could get that. And really then it's just a computing power. You just don't have it. But if you think, what computers were in the 70s versus today, so you can see how things can progress. So it could be that in 10 years, maybe 5 years, you'll be able to build your own. I don't know. I can't tell you that. Yeah, go ahead.
Do you think quantum is going to make that?
It's like, don't ask me about quantum because I can't, I don't know what to say about quantum, to be honest. Um, it doesn't exist yet, right? Quantum is theoretical. It's still in the research state. They're always saying they've made an advancement. Maybe true, maybe it's not true. Maybe it's like fusion energy. Yeah, fusion, right? It's always just 10 years away. Always just 10 years away. Then again, I mean, they could have I thought the same thing of AI. So if you think about it in 2011 or 2010 when I was doing I just thought, okay, this is a nice career. I'm just gonna do papers until I retire. It's gonna be so much fun. We'll never get to anything. And then now it's like, should I change research areas? Because it's solved. You know what I mean? Like they've actually built the thing that I never imagined they would build. Do you see what I'm saying? Like I was in 20, people in 2008, 2009, we were trying to say if a sentence was happy or sad. You know what I mean? And think of where we are today. So I don't know. I mean, if you're a person that is worried about, you have to like hedge your bets. So study quantum and hopefully you'll be well positioned. But I don't know. Like quantum does not work exactly like regular computers, right? So it's good for certain tasks, but not for everything. Yeah. It's right now, quantum is good at like simulation. Like if you want to simulate quantum. So for instance, if you have a process where it's important for you to understand how molecules evolve to create some kind of material or thing, well, that material is quantum at some level, right? So then you can simulate it with a quantum computer. They're good at breaking cryptography, but machine learning, I don't know. Maybe. I don't know, but it's not something that I'm worried about it because I really don't want to have to relearn all this stuff. But I don't know. Did I answer your question?
Yeah.
Yeah. So I don't know. But anyway, so I think I was talking about the homework, was I not? So that's what I want you guys to kind of think about right now, right? So we're gonna start today with our first actual big algorithm, transformers, encoder, decoder, and from that, the GPT. We'll start with the basic operations, but you will have two assignments, which are essentially to train oh yeah, what I was saying is don't expect it to work that well, right? Because you don't have enough data, you don't have enough computing power. You'll be using one GPU when these companies, OpenAI, Meta, are using thousands of GPUs. They have all the text in the internet, all the books, right? So, but it's a good exercise to go through just to see how difficult it is. And also, as I said, you never know, 5, 10 years down the road, you may be able to do this because there's some advancement or something like that. So we want to understand it. And by understanding this algorithm, it'll help you to understand PyTorch in general, quite a bit of the complexity. So that when you build a normal, simple neural network, it should be pretty easy. All right, so last semester, the first assignment that I gave, or last year, was to build a crawler or a scraper to just download text data, okay? Last year, I gave everyone one website, which was a veterinary-related website of information, and they downloaded it, and then they built a vet GPT, if you will, right? So that was the idea, a veterinarian GPT. But this year I'm gonna make it so that more open-ended, so you can pick something, but just keep that in mind, right? That I want you to build a GPT for some task, like a vet GPT or a chemical engineer GPT or a musician GPT, whatever you want, build it. Okay? So just decide what you're gonna do. So that means you have to download text that's all kind of related. Do you see that? And you can go to multiple websites also. Last year, I just gave one big website, but this time around, you can go to as many as you want. You could build a really nice platform that collects a lot of data. Just keep in mind, all that data needs to run on GPUs. And so how many GPUs will you have, right? So so essentially, I think everyone will have just one. And so you'll see how long it takes to train and all of that. Does that make sense? And you're training the model from scratch, right? So it means that initially the weights are, just random weights, and then you're gonna be updating. Okay. So obviously I'm breaking it in two assignments. So one is going to be just the scraping of the data. Okay. So you'll build, the scrape, you can build however you want it. So I'm not, use tools or whatever, crawl or scrape, but essentially we don't need the HTML, right? So we only need the text. So the HTML actually would confuse the model unless we were building a GPT to create websites, right? But that's not what we're creating. Does that make sense, guys? So any questions on that? That's going to be assignment number one. And I'll be creating that shortly. Yes, please.
How much time then?
Yeah, that's a good question. So like 2 weeks. So, there aren't that many homework assignments in this class. So I think before week 8, I really want to do that and the LLM essentially. So it might be those two. Yes.
Submit.
I'll create a link on Brightspace and you'll submit a report, but you have to you have to download the data, right? And have it available so that you can, on the second assignment, train an LLM.
So what would be the typical?
It's up to you. The bigger the better, but also, the more data you have, the more GPUs you need. So it's a problem where you have to find a balance. Like you could spend all this time downloading terabytes of data, but then you won't be able to use all of it. Do you see that?
Training all the data to create.
Yeah, because you need more time, more GPUs, more things in parallel, etc.
Okay.
It's up to you. There's no requirement. Well, that's kind of the thing that you want to understand, right? That, yeah, I mean, if you think about how these models, they use the whole internet, basically, all the books, right? But that's a lot of data to train. So you would need lots of GPUs. It just, yeah, processing. So you have to kind of just think about those two things together. Okay? Yeah, the script itself. And actually, what I like to do is I like to do presentations. So we'll do a day when you guys come up here and do your presentation and you will demo your GPT. So the code I'll give you works fine and you can ask it questions. So it's already made. So I'll show you the whole process, even to the point of how do you ask it questions, and it'll work. Just
Train.
Yeah, you'll train it. So I'm going to talk about that second part in a second. But yeah, I'll give you the code. It's from scratch in PyTorch. And you will take all that data that you downloaded and then train your LLM. And then once it's trained and you have a model, you can bring your computer, right? And you can ask it, questions and things like that. Got it? All right, great. So, as I said, last year everyone did a vet GPT, and because I was interested in seeing, how good we could do that, this year open-ended. So pick a topic of interest to you. You want it to, be like Shakespeare and talk that way, or something like that. Go ahead and pick. But yeah, you'll build a scraper. All right. So no questions on that one, I assume, right? So I'll create the link. And describe it there on Brightspace. The second assignment then will be, once you've downloaded all that text, you will go ahead and train a large language model. So I can tell you right now, this repo has everything you need. So it'll be this one, GPT Scratch Huck Finn. You see that? So this one I've created. Here's the Huck Finn story. So I just grabbed this book from the Gutenberg.org. It's The Adventures of Huckleberry Finn. So you can just, this code is made to just grab that file and you train it on it. Obviously, what you guys have to figure out is how to give it more, right? So you would give it more books or more text, etc. And the code is written in such a way that, you can train and then you can, in inference mode, ask it questions. Okay? Got it? So the code works fine. So there's not really much you have to do, but most of what we're going to do for the next couple of weeks is try to understand this code, right? So we're going to, my goal is to explain to you how this GPT works, right? And, all the details of it. All right. And then when you do your presentation in a few weeks, so that might be in 3 weeks or 4 weeks, you'll come up here and you'll say, I did a GPT that's like Shakespeare. So here's some examples, and then here's a few questions. Just to give you an example, when we did the vet GPT last year, we would ask it, okay, some kind of thing, I have a dog and it's sick. These are the symptoms. What do you think it is? And so it would answer. It would try to answer. It wasn't perfect, but do you see what I'm saying? So that's your objective. How do I make it as good as possible? So, and then that's, there's a lot of things that you can do with that, play with it, and especially trying to understand how the algorithm works. Okay? All right, so those will be the 2 homework assignments that we will do. Okay, so yeah, so this is the code for GPT from scratch, Huck Finn, and this is the one that you will use. What I'm going to do today is I'm just going to go over the other scripts that I have here or examples. So I have taken this script here and broke it up into, the different parts, and also created a much smaller version of it, which I'm calling the baby transformer. And it's just like I removed a lot of things, a lot of simplifications, and I just left the basic things that you need from beginning to end to be able to get the data flow through it. Okay, so so this lecture is how LLMs work under the hood. Okay, and this link just refers to another repo where I have additional scripts, but you can start here. The first thing we're going to cover today is the dot product example. So going back to tensor operations, right? So the difficult thing about understanding really a large language model or a GPT is that you start reading through the code and then you encounter this tensor operation. Is like, what is going on here? And from there, you're just confused. Do you see that? And so what I'm gonna do is we're gonna go over the basic operation, which is the matrix multiplication, and you will see that that's essentially everywhere. Okay, it's in normal neural networks, it's in CNNs, it's everywhere. But it is the fundamental operation of deep learning. Okay, so we'll go over what is a dot product. Then after that, we'll go over the matrix multiplication, which is essentially using dot products, right, to do the operation. So we'll go over that. So the matrix multiplication example in PyTorch, we'll go over this. We'll see how this ties to vector spaces. If you remember, I talked about vector spaces a couple of weeks ago, and we're going to tie it back to that, why it matters. Then LLMs under the hood. So we're going to talk about understanding the attention mechanism. So maybe you guys at some point read about ChatGPT or transformers, and you read somewhere that there was this key operation called attention, right? Which is pretty important. So we're going to talk about that, and we're going to see mechanically how it works, okay? Mechanically how it works. That's one of the scripts that I have somewhere in there. Yeah, so this is just that. And then here you are, the baby transformer. So this is a proper GPT, right? So the GPT is no secret. Everyone can have I have many copies of the software, right, for a GPT. That's not the difficult part. The difficult part is the data and the multiple GPUs, right? So if you had, that's why I'm saying if in 10 years, I mean, we could all get just like a thing like this, that's $2,000 and it's powerful enough to run all the data. Hey, we would all be able to train our own GPT or pre-train. There's steps after the pre-training, fine-tuning, reinforcement learning. Those are actually topics I cover in 530, right? In this class, we only cover up to pre-training. All right. Yeah, so yeah, this is a baby transformer GPT style from scratch. And you can see, believe it or not, that's the whole code from beginning to end, right? So this is the most simplified version that I could think of for a GPT, like Chat GPT. So I think if you really understand this, in detail, you'll see that it's a very interesting idea, okay, to train a large language model. All I'm doing today, by the way, is the inference part. So that's essentially like the neural network architecture that takes inputs and produces an output. Okay, that's all I'm doing. Remember that in all neural networks, we build that and then we still have to train it. So I'm still going to be using random weights and I'm not going to be doing any training. Okay, it's still just the architecture itself. Okay, and so that's going to be the baby GPT. Yeah, and that should be it. Okay, any questions? All right, great. So we're gonna start with, the dot product, right? So we're gonna start with this operation. I'm gonna go to Colab, and that's probably the easiest way to begin. And I've demoed Colab already in this course, right? Yeah. Remember, I'm teaching this class for the other section. I get confused sometimes as to what I've done. So tell me if I haven't. But yeah, so we're just going to do a simple collab here. And remember, you can try to train the LLM with a GPU and, just change the runtime to have a GPU. All right, so here we are. All right, so the first operation, as I said, is the dot product. Okay, so dot product example in PyTorch. So this is the minimal example that demonstrates how to compute the dot product of two vectors using PyTorch. Remember, I've said many times when I talked about tensor operations, we can't just do things on a variable basis, right? Like, hey, I can't take a variable of equal 3 and a variable equal 5 and multiply them and then multiply another one and another one in a CPU fashion because it would just be too slow, right? So we have to use linear algebra, which is the basic concept, so that we can do parallel computing, right? So imagine multiplying multiple variables at the same time. And so the key thing we want to understand is how this dot product operation works, which is this code here. So I'm going to go ahead, I'm just going to copy it. Yeah. So, sometimes you look at a topic and you see one operation and it's difficult, and then there's like another operation and it's difficult and different, and then there's like 30 others and they're different and difficult, right? The nice thing about this is that while these might be difficult at first, there's only like one or two operations, right? And that's it. So that's kind of the beauty of this. So let's look at the dot product first. So I'm going to go to Colab, go down here. And I just like I did with the tensor operations, I'm just going to mechanically describe it, right? So these are operations from linear algebra. We don't have to know everything about linear algebra, just these basic operations. So I'm going to, jump straight into PyTorch. I'm going to run PyTorch. Give it a second there. Okay. Okay, so I'm gonna do this while it's doing. Okay, and it finished, so we've got our library. Now, the first thing I'm gonna do is I'm just gonna grab a tensor. Okay, this is a vector. So the key thing when you're multiplying, and I'll show you how this operation is computed, but essentially the dot product, you define two 1D tensors. So they have to have this, they have to match in dimension, okay? So here we have 3. The dimension is, the size of the vector is 3, and that's A, so I'm gonna just run it. Okay. I look at the value, but also I can print the shape. And you can see it's of size 3. Okay. Then the other vector that I'm going to use to do this dot product has to match in size also. So this is B dot shape. Okay. And I'm going to perform the operation. And you can see it's also of size 3. So this is 4, 5, and 6. So once that's done, I'm just going to perform the actual operation here of the dot product, which is going to be torch dot A and B, right? So I'm going to perform that, and you'll see what happens. This essentially creates one number, which is 32. Okay. So how does that work? So it's in the repo. You can see this gives a 32. So this is the explanation of the dot product, right? So the dot product of two vectors, guys. So the dot product of two vectors is calculated as this. So I'm going to copy, I'm going to go to the code, and you can see that the idea is that you will multiply 1 times 4, right? Plus 2 times 5 plus 3 times 6. And that's the operation always. That's it, right? That's a dot product. And that's going to be like one of the part of the matrix multiplication. Okay, we'll just have more vectors in there. So let's see how that works. You can see I have it here. I'm going to make this a little bit bigger so I can see it better. So that you can see it's 1 times 4 plus 2 times 5 plus 3 times 6, right? And that should equal 32. So if I run this, you can see it is 32. Does that make sense? If I could do the same if I had another vector, just, they just have to have a matching size. So for instance, 7 and, 5. You see that? So now they both have size 4, 4, 4. And then I just perform the matrix multiplication. You can see it is now 67. Okay, they just have to match. Okay, so the dot product is like the fundamental operation. And that now we're going to talk about the matrix multiplication, which is made up, you can say, of dot products. Okay, and this is the fundamental thing that happens in neural networks. Okay, a neural network from one layer to the next, it's essentially a matrix multiplication, as we will see today. All right, so I've done the dot product. So now let's go ahead and take a look at the next part. All right, so we can see here, torch dot requires both inputs to be 1D vectors of the same length. For matrix style multiplication, we will use torch.mapmul, which implies matrix multiplication. This, I like to use this term, but you can also use the @ sign in PyTorch. It's the same thing. So now take a look at this one over here, because this is pretty fundamental, right? To me, this is like one of the key things. Now, you guys remember the iris data set, right? So what was the iris data set? Fisher's iris, 150 samples. How many features? 4. And then I have how many classes? 3, right? So keep that in mind, because if you look at the dimensions of this, that's what they are. This actually ties back to word problems. Remember, I said X and Y, right? And I wanted you to give me the shape of X, the shape of Y. So in this case, think of this one as X, and the shape of it is 150, comma 4. What does 150 mean? It means samples. So 150 samples, and 4 means 4 features, right? Sepal length, sepal width, petal length, petal width. This is just, I'm using that example because it's familiar to us, but you could use images, you could use whatever you want. Okay? So here's the key thing. If you look at the matrix multiplication, it's just made up of dot products. So a dot product was just a multiplication of two vectors that had equal size, right? So notice over here that I have this matrix that is 150, comma 4, and I have this other matrix that is 4, comma 6. You see that? And the key thing is that this has 4 in the, 4 columns, and this has 4 rows for one single vector. Do you guys see that? So then you should intuitively say, okay, I can do a dot product between those two if I want to. So I can take this, notice that I have this blue line, right? So I do this one, blue line, this one to produce just one little value that goes there, just like I just did with the dot product. Remember, I had two vectors, but they just produced one number, 67, I think it was. Now I do the same thing. I can grab this one again. Notice the green line goes to this next one that is also of size 4, do a dot product, and the resulting value goes there. Let's say 58. Do you guys see that? So that operation is pretty great because it allows us to transform. So hence the name transformers, which are the GPT. So transformations just means doing something like this. We take some data like this times a matrix multiplication to produce another representation of it. If you look here, this is 150, comma 4 multiplied by some matrix that I design, and that produce the 150, comma 6. Do you see that they do have one thing in common, right? What is it? They have the same number of rows. Do you see that? So think of that as the first 150 samples I had, I still have them, but I just transformed them. So it's like if all of you are in this room, right? And this is a vector space, and you're holding a tray with 4 glasses, right? But you're still you just hold 4 glasses. Now I'm going to take this matrix multiplication with some matrix, and after that operation, you're here, you're still the same 150, but what happened to your tray of 4 glasses? It is now a tray of 6 glasses. Do you guys see that? That's the key intuition here. You can do this transformation. The values don't matter at this point. They are still random values, but the operation is pretty important. How are the values modified? The values are modified when you do the matrix multiplication, but when the values in this are actually the correct ones. Initially, they're just going to be random. But that's where the second step in training comes in, because as you start, predicting, comparing the error, back propagating, what you're doing is adjusting these values. But that only happens during the training. And that is actually the intelligence. I make the joke all that, well, some Elon Musk actually said this, but he said, the thing that the Terminator, right, that's going to kill us all, that everyone's afraid of, is really just this matrix of weights. Because that's the intelligence, actually, right? Everything else is the architecture, but this matrix, we just define like the architecture and the multiplications. During training, these values are going to be populated. And that's what the intelligence is. Does that make sense so far, guys? Any questions? So this is essentially what we're doing, right? So we're learning that we can transform our original data, 150, comma 4, by doing this into 150, comma 6, So what if I want to change it to 150 comma 8? Well, then I just add two more vectors here of size 4. Do you see that? That's it. That's like the nice trick about this is that, and this translates also to the neural network itself, as we will see in a second. But it's essentially a matrix multiplication that is happening. So again, I'll repeat. So if this is 4, this has to be 4. Because otherwise, like it won't work. And then the 6 here just depends on how many new columns you want to represent that space. All right? Yeah, go ahead.
That's the one I still don't get. Like,
Yeah.
why do we choose? Like, we wanted 3 classes.
Yeah.
So why did we choose 6 just because we multiple 3 and it worked out? Or
No, that I actually like your question. Let's switch over to the whiteboard because we're gonna do that, but it's a good question. So you're already thinking ahead. So your question is why 6 and not 3? Because really 3 is what you're looking for in the end. So let's look at this here. So I had 150 comma 4. Remember that this is a vector space, right? We've talked about this. This is R4. So essentially there's 4 axes that are like 90 degrees. So that's 3. We can visualize that. And now you just have to use your imagination that there's a 4th one. But I actually want to transform this by doing a matrix multiplication into another vector space. So I'm going to say 4 comma 6. So essentially what I'm doing is I'm going to produce a space where all 150 of these live, but that space now is R6. So it's going to be 1, 2, 3, 4, 5, 6, where they're all perpendicular, 90 degrees. Everyone agree with that? That's exactly. So this, essentially we're putting our values from a vector space that we knew, petal length, petal width, sepal length, sepal width, into this new space of 6 latent dimensions, but we don't really know what they are anymore. We're just telling the GPT, hey, use 6. And the GPT is like, okay. And then how is it going to learn? Because when you give it the data, it's just going to fill it up randomly, right? And when it does it in one way, the results are bad. So what does it do? It changes the weights to another set. And then that's bad also. And then it just keeps doing that, right? Obviously, we want to do that in a smart way. So that's why we have stochastic gradient descent. And eventually that algorithm, boom, gives us the nice set of weights that when we do that, we can classify our images into a cat or dog with 90% accuracy. Do you see that? So so it creates just latent 1, latent 2, all the way to latent 6. Why latent? Because we don't know what they mean. Like semantically, we don't know. But as it turns out, right, with the flowers, maybe it discovers that a better example might be, or easier example to visualize is cats and dogs, right? So in cats and dogs, we might have the original images, but over time it learns that latent 2 somehow can pick up something about how furry the animal is. That helps it to classify one animal or size. Cats are usually smaller than dogs, right? So that might be, so somehow it figures out a new feature, L2, which represents size, but it just statistically figured that out. Do you guys understand? So it creates these new spaces of representation based on, the data and, having some kind of loss function and minimizing that error, essentially. Okay? So yeah, go ahead. And I'm still haven't gotten to the end to your answer, but what's your question? Yeah. They're they're matrix multiplications of the previous ones. So essentially here, you're just creating you define that you want this space to be 150 comma 6. But these values, imagine they're still random. So during training, though, you have to think that the data is flowing until coming out to the final prediction, and that final prediction is compared to the real data. You minimize that error, and via stochastic gradient descent, you backpropagate. So when you backpropagate, you change these values. So correlation is part of it, but the correlation is where in the prediction versus the real, this comparison for the error calculation. That's where I would say it is, right? But the stochastic gradient descent essentially just updates weights. And it's going to update them to things that provide good results. Do you see what I'm saying? Yeah. All right. So to your question, right? So all I did is I took 150 comma 4 times this thing to produce 150 comma 6. But you're like, what I want is 150 comma 3.
Well, I guess I'm
Uh-huh.
talk about that. I'm just wondering, like, you can say, the bigger.
Yep. Mm-hmm.
Why did you 6 instead of 5? Is it just a number that we try and see how the engine works, and if it sinks, we try a different one?
Pretty much, yeah. So here, I'm going to do this now with the network, right? So 150 comma 4, right? This 4 means 1, 2, 3, 4 neurons, the input of X. When we convert it into 150 comma 6, it's not the final layer. It is just a stepping stone layer. But that 6 means 6 neurons. So that essentially is just an intermediate layer, which we call a hidden layer, like hidden 1. Okay? Then what you could do is you could take this 150 comma 6, multiply it by 6 comma 3, and guess what that gives you? That gives you 150 comma 3. And so that means 1, 2, 3. These are actually the classes C1, C2, C3. So you do that operation to create the entire neural network. All right, so that's essentially what is happening. I'm simplifying some things, like there's going to be like ReLU activations and things like that in here, but let's ignore all of that for now. Okay, so the tensor operations are just mapping the space. I could have chosen 8 here or 60 for that matter. It doesn't matter. If I choose 60 here, then this is going to be 60. Do you see that? It's just, yeah, go ahead. What do you mean the logic of? Why 6? Why give it 6 or 60? Yeah, exactly right. So it's, usually there's no science to this. It's experimental, right? But there's some rules of thumb. So for instance, if it's a really large image in the beginning, right? 28 by 28, which is 784, almost always you actually funnel it to something smaller. Do you see that? So every new layer would be smaller. Like this one would be 100, this one would be 40 or something until you arrive at the 3 classes. In something like Iris is kind of difficult, but what I would say is if I start at 4, I'll probably go up to 10, and that's it. You could think of it as having more options. So the idea is like this. Sepal length and sepal width somehow together are good. They provide additional information. So then you do that. This neuron activates when both of them are present or both of them are above a specific value. Do you see that? So that's the intuition. So a better intuition might be with images. So I'll give you this. I use this example sometimes. Imagine we're doing images. All right, so we have this, that. Then I have another layer and another layer and another layer, right? So in the first one, all that I capture is like little curves. So I have this little curve and that little curve and that little curve like that. So I have a curve that's, imagine this curve is this one, and this curve here is that one. It just picks it up. And then there's a neuron that kind of captures when both are present, it fires up. So what did it find? It found that and that. But then there's another set of neurons that capture kind of these curves that are, these are vertical and the other ones are horizontal. Do you see that? So that might be this neuron, and that neuron captures those green curves. So what happens then? There might be an intermediate neuron that captures that. And obviously this is starting to look like a circle, right? So then there might be a neuron over here that captures both of those. And you can call this one a circle detecting neuron. But that was, imagine, you needed 3 layers to find that. If you only had 1 layer, you were just capturing independently vertical or horizontal curves. But as you add more layers and more neurons, you might actually pick up circles. Now, what if you have, like eyes, right? So then you might have some other flow of neurons that comes over here, and now this layer picks up that there's 2 of these, and now you have a face detection algorithm because you have eyes, so you know where the faces are by just finding this. But it's a combination of the things that you're discovering. So images are usually better for this type of understanding. Does that make sense? All right. Now did I answer your question? So the reason why we built, I was here, right? So we're doing the matrix multiplication just so that we can transform that space of 150, 4 to 150, 6, 150, 80. You add as many layers as you want, but in the end, you want 150, 3. This is essentially now you're saying every one of these samples is a vector of 3, right? And there's values here, like these are 0.20, 0.20, 0.20. At this point, this is the prediction. So that prediction is compared to what? To the actual data. So in a 3-class problem, you know that it's one of the 3 classes. So let's say it's the 2nd class. Well, that's the 2nd class. Do you see this? So now what you do is you compare this vector to this vector and minimize that error. So obviously this error is pretty high right now, right? Because this is like terrible. What's going to happen is during stochastic gradient descent, the weights are being updated. So eventually, maybe this is like 0.6, and no, let's say this is 0.6. And this is like 0.2, and this is 0.1. You can see it's starting to approximate 0, 1, 0. Now it is 0.2, 0.6, and 0.1. This is starting to be like the dominant one. Do you see that? That's what's happening during stochastic gradient descent. Those values are changing because the weights in here and these here are improving. They're not random anymore. Until your goal is that eventually, guess what? These predictions are going to be 0.01, 0.01, and this one is 0.98. That is effectively 1. So you have a perfect error. Do you see that? So one thing creates the architecture that allows you to move the vector space from one to another. with random values, and then stochastic gradient descent allows you to update the weights themselves. Any questions about that, guys? Yeah, go ahead, please.
Data transform, but
And what? In graph neural network? It's a matrix multiplication. You will see it in the there is a graph, I guess, but it's a graph of matrix multiplications. So what do you mean? It's like this. It's a matrix multiplication, right? So it's like, you can think of the network like this, like a graph, right? We can think of it like this. But essentially, as you look at PyTorch, it is essentially you have a weight matrix times the X matrix times a weight matrix to produce the output that it is, which is another matrix. Which graph? Like which graph are you talking about? You mean this thing that I was drawing here? This? This model, or do you mean the computational graph maybe? Something like that? All right, give me a sec. So there is, when you build PyTorch or TensorFlow, there is a computational graph involved. That's like the classic idea. So TensorFlow is called, it means flow of tensors essentially. But what you do in that computational graph is you create a matrix, let's call it X, and then you create another matrix, this is X, called a weights matrix. And then there's going to be an operation, which is the map mul. And when that produces, let's call it the Y matrix. Do you see that? But essentially, it's just this matrix multiplied this to produce that. So from one tensor to another tensor. So that's what's happening in the computational graph. This thing that I drew here is just because this is how we see a neural network. Like the idea I'm taking, notice for instance here, I don't have the 150 sample. So I just look at the previous one was vector of 4, right? And then vector of 6. But I've simplified it just to like visually imagine what's going on. Do you see that? So when we start looking at the code, you'll see that the operations are just matrix multiplication, okay, for the transformation. Do you have an additional question? Let's take a look at it and come back to it, all right? So, but yeah, so this was the logic. So let's go back to, so we went through this operation. So I think you guys get it, right? So this is the matrix multiplication. And here it is, right? So let's where is it? So I did the dot product, and then yeah, so we're gonna do this one. Okay, so I'm gonna remove torch. Okay, so I have X, which is, as 150 comma 4. Okay, we can look at the shape of it. 150 comma 4. I literally create another matrix which is a weight matrix with random values. Remember, all these are random right now. Do that. And then I perform a matrix multiplication as I just showed, and that produces this Y dot shape. And you can see it is now 150, comma 6. But then I can do another one. So I'm just going to change this name to H1. And I just essentially made it a hidden layer in the network, right? H1. There it is, 150, comma 6. Now I want that outer layer, that last output to the classes. So what do? I'm just going to create W2, let's call it, right? And it's going to be just like the previous one. What are the dimensions of this one? What, instead of 4, 6, very good. And for this one, 3. You see that? So that's, but let's say I want a second hidden layer for some reason. And I want it to be 12. Guess what? There's my second hidden layer. And guess what? I just made this deep learning. Pardon? Yeah, 12 is the question he had. Why 6? Because I want to. I can make any number I want. Now, should I make it 3,000 when it's the Iris data set? Probably not. That's like, first of all, it's too much on the GPU because it does have to compute those weights, but also it's a waste, right? So for something as small as Iris, okay? So here I'm doing W2 612, correct, guys? Do you see that? All right. So I initialize that. I have 2 equal signs there. All right, great. I have my, and I can probably do W2 dot shape. So I just built an input layer, 2 hidden layers, and now I want to finish it up with a final layer. So what do I need to do? Before that, I need to make this matrix multiplication, right? So that's going to be what? The first one was H1, so let's call this one H2. Do you guys see that? H2 is, should this be X? H1, right? So this should be H1, very good. And this should be W2 because it's this other weight matrix that does the transformation. And now this is H2. Boom, 150, comma 12. I just created another vector space, or another analogy is I just created a second hidden layer. And now I'm going to proceed to do the final layer to the output. So that's going to be, I need what? What do I need? What's the key? I need another weight matrix. Let's call this one Y3. What's the dimension for this one? 12, comma 3, correct? Because there's going to be 3 classes. And I just defined that. And then, of course, that needs to match whatever my labeled data is, you know? So in Iris, I have 3 classes. So then I do this matrix, that's W3, run it, there it is, 12, 3. So now all I have to do is my matrix multiplication. So that's going to, this is finally Y, mapmul H2, correct? Because it's the previous hidden layer. Multiplied, matrix multiplied times W3, that weight matrix, and that should produce that. 150, comma 3. What does that, so going back to graphs. So in Torch needs to create this thing called a computational graph, but that's what it's doing internally. The moment you import Torch and you start doing all these things, imagine it's doing all of this internally. Why is that necessary? Because of the gradient descent. It needs to know, like, it started here and then it went here and then here and then here, because once I calculate the error, I need to go back and update all the weights. You guys see that? So that's one graph. But this one is more of intuitively for us to understand, right? So let's see what this graph would look like. The one I just did with matrix multiplications. what does it look like? That graph was 4 initially, right? Because it was iris. Then I did a matrix multiply for 6, right? So that gave me 1, 2, 3, 4, 5, 6. That was hidden 1. This was X. Then I did another one. I called it hidden 2, and it had 12, right? So 1, 2, this is 12. And then the final one had 3. So those operations I just did create a neural network that looks like that. But this is more of like intuitively for us to, think of a neural network. But my point is from here to here, there's always a weight matrix and a matrix multiplication. So this matrix multiplied this gives you this. This with this set of, now you have another weight matrix here. So this matrix multiplied this gives you this. And then I have another weight matrix. This matrix multiplied this gives you this. Okay? Right now, the weights are random. So it's gibberish what's coming out. But during training, we're back propagating to update the weights. That's another thing. That's like the second part. Stochastic gradient descent. Make sense? Any questions, guys? Questions? All right. So now we've done that. We've completed that example. Very fundamental, right? We're going to repeat this again when we look at the attention mechanism in a second. So, but let's go back to the repo. So we just completed this one. We talked about these dimensions. So why does it matter? This is the core. This is the core of how neural networks compute outputs, okay? A layer transforms input features into a new representation by multiplying by a learned weight matrix, okay? This example is the essence of this formula, which, yeah, go ahead. So weight matrix, so yeah, good point. So what I've been doing is just multiplying by a weight matrix. I didn't do yet multiplying by a learned weight matrix because the values in these matrices, weight matrices right now are random. So learn would be when they're not random after training. So if you build the architecture of a neural network without training, you can give it inputs, it'll give you outputs. They're just random. But once we see the training itself, right, then that matrix has the correct weights, and now it'll predict whatever you want it to predict. So that's what it means by learn. You have to train it. No, I mean, you literally have to write the code for training, which we will do. Yeah, go ahead. Think of it as I build all like the pipes. I put a pipe here and a pipe here, and it goes up and down and all these pipes. That's what I'm doing right now. But I haven't run any water through it yet. Do you see what I'm saying? Once I run the water through it, then I'm going to have a process of like filling in the missing part. But I'm just building this architecture with matrix multiplications. Yeah. Yes. Yes. Then to the final layer 3. Why did I do 6 and then 12? Well, this question was already asked, right? So I did it in the whiteboard. Remember, this is the example I gave with the eyes. Why do we add more layers? Remember, I gave this example, the horizontal curves versus the vertical curves. So then this one finds when there's 2 horizontal curves, this one when there's 2 vertical curves. but there's a neuron that lights when both are present. So now you have found both horizontal and vertical curves. And if you think about it, that starts to create a circle, right? Because you have this one, this one, this one, this one, right? That's a circle. So you would not be able to find that circle if you just stayed here, because this just finds little curves. But what you're trying to find, let's say your problem is face detection, right? Well, most faces have eyes in them. But to find the only this neuron here finds two eyes. This one finds one eye. This one here just finds vertical curves. This one here just finds horizontal curves.
So. You do this.
We give it more capacity. Like the intuition is, if you give it a deeper network like this one with more neurons, is that one layer finds like very raw things, but it transforms them into something more meaningful that can be used by the next layer. And then the next layer transforms it into something more meaningful that can be used by the next layer. So that's why you add this and you make it a deep neural network. Think of language, right? Language comes in, but you have to semantically try to understand that language. So the transformer, for instance, is a very deep neural network. Yeah, I mean, yes. So we will learn. This is why we're learning these algorithms. So you will learn as we start to, get to images, for instance, that you want really deep neural networks that use something called a CNN, but they're deep, right? ResNet 50 means 50 layers. Do you see that? And that has been shown to be the best. It took like 5 to 10 years to build ResNet 50. You see what I'm saying? People try until they have found one architecture that works well. There's only one. I don't know if you guys know this. Maybe you don't know. I don't know. That all LLMs are essentially the same architecture. It's not like Meta goes and, oh, we did this and ours is like this. And then OpenAI, ours is like that. They all literally have the same architecture. It's fascinating that they invented it in 2017. It is now 2025, almost 8 years later, and it's almost exactly the same architecture. In fact, I think they're like terrified of changing it because, well, first of all, it works, but also they just don't understand it. It's one of those things where it takes a little bit to understand. Just to make you guys have generated images, I assume, at some point, right? Those are stable diffusion models. They're a specific architecture that took 5 years to perfect, but it's still pretty much the same idea. Yeah, go ahead. DeepSeek, okay, got it. Yes. Yeah. Yeah. Mm. No. So actually, like DeepSeek, one of the things DeepSeek wanted to do is they want to be able to think about their logic, right? So they want to compare themselves to the state of the art. So they want to compare what they did to the state of the art, which is ChatGPT, Meta, and so on. So they actually did it in such a way that they can still use a llama, for instance. What that means is, and llama is built on like the normal architecture. So they can take the normal architecture and add on to their stack. Do you see what I'm saying? So they're still using the same LLM. What's changing is, yeah, some of the pre-processing is very efficient, right? And the way that for instance, the way that they wrote the C code, right? And how they use the operations at a very low level. but the architecture is the same. And one of their innovations was actually in the fine-tuning process. They have their own, later on in 530, you guys will learn that there's reinforcement learning through human feedbacks, and there's several algorithms there for that, but that's more of a optimization loss function versus an architecture. Do you understand what I'm saying? So architecture is what we're doing right now. These matrix multiplications, so they are using attention, right? They might use a modified version of attention, but they are using attention. They are using all these blocks. They are using positional encoding. So they're using a lot of the elements of the LLM. Do you see that? Their innovation was, once you pre-train the model, you do fine-tuning, DeepSeek. And they had a loss function called GRPO. That was actually, if you look at their papers, most of it is that GRPO thing. Okay, so yeah, good.
Not sure who are using to train.
They can use a pre-trained model such as Llama and add it into their stack of DeepSeek. Do you see that? That's actually something they wanted to do. So they actually, a lot of people do this. They pre-train their own models to show that they can do it, but they also want to stand on a pre-trained model of someone else. Because an LLM is more than just a pre-training. There's like fine-tuning, reinforcement learning, and several other steps. ChatGPT is not public, but go ahead. You can, yeah. The Llama, Meta has created pre-trained LLMs that everyone can use. Open source, yes. For research, you can't use it for commerce. Like if you can't start your own business because it's theirs, but you can use it for research. So something like DeepSeek, they can, that's what I was saying. They can take Llama 3.2, the pre-trained model, and then they do their own stuff to it, but they also choose to pre-train their own model. They did do innovation in data processing, and also what you're missing is that GPUs run on C, C++, not on Python. And so our Python and PyTorch gets compiled to C. And what they did is they somehow rewrote that C code to be super efficient. But that's like a different thing from creating a neural network. That's like they just, because this gets into geopolitics and things like that, but they don't have A100s in China. They only have H4s or whatever, H20s. Okay, so then what do they have to do? You have to work with what you have. And so how do you squeeze more out of an H20? By going into the C code and modifying it. So it's not the architecture of the neural network. It's like at the C level, the hardware, as I said, because you compile the Python or PyTorch to C. Does that make sense? Yeah. But yeah, no, these are really good questions. But and I can see you guys, you should be skeptical, right? But I'm telling you, it's interesting that everyone just uses pretty much the same architecture from the original 2017 paper. That's how amazing that was. All right. All we're doing is the architecture right now. A large language model takes a little bit to build. But yeah, this is the fundamental operation. Got it? All right. So yeah, so great. So let's what time is it? So it's 7:50 actually, right? Is that 7:50? Yeah. So this class started at 6:30, 7:30. So it's an hour and 20. So let's take a 10-minute break, and then we'll pick up with getting into the algorithm in 10 minutes. Yeah, let me just end this.